Vector embeddings are the digital fingerprints of information. By converting complex data like text or images into lists of numbers, we create a mathematical representation that machine learning models can process with precision. Vector databases function by indexing these numerical lists in high-dimensional space. Unlike standard storage, they are architected to organize data based on its inherent meaning rather than just its file structure or label. Similarity search operates by identifying nearest neighbors within this space. When you query the system, it maps your request into the same coordinate system to find the data points that cluster closest to your input. Traditional SQL databases struggle with semantic search because they rely on exact keyword matching. They cannot interpret the underlying intent or context, making them ineffective for finding concepts that are related in meaning but different in terminology. To bridge this gap, we use distance metrics like cosine similarity to measure the angle between vectors. This calculation determines relevance by identifying how closely the direction of two data points aligns, regardless of their absolute magnitude. We begin by downloading the Qdrant vector database binary. Using curl with the silent and follow flags, we fetch the compressed archive directly from the official GitHub release page. This ensures we have the correct version for our Linux environment, setting the stage for a local deployment of a high-performance search engine. Next, we extract the contents of the tarball using the tar utility. Once unpacked, we use chmod to grant execute permissions to the Qdrant binary. This step is essential to ensure the operating system can run the application as a process, preparing our local environment for the database initialization. Now we launch the Qdrant server in the background. The terminal displays the startup logs, confirming that the service is initializing its storage and setting up the HTTP and gRPC interfaces. By running this in the background, we keep our terminal session active for subsequent API interactions. With the server running, we verify connectivity by querying the collections endpoint. A successful response indicates that the REST API is responsive and ready to accept commands. This is a crucial sanity check to ensure our local instance is fully operational before we begin creating data structures. We now define a new collection named demo. We send a put request with a JSON payload specifying the vector size of 3 and the cosine distance metric. This configuration tells Qdrant how to store and compare our upcoming data points, establishing the schema for our vector search operations. It is time to populate our collection with a data point. We send a put request to the points endpoint, including a unique identifier, a three-dimensional vector, and a payload containing a title. This structure allows us to perform semantic searches later, linking our vector data to meaningful metadata. Finally, we perform a search query. By sending our vector to the search endpoint, we ask the database to find the most similar point. The output confirms that our system successfully retrieved the data we just inserted, demonstrating the core functionality of vector-based similarity search in a production-ready environment. To conclude our tutorial, we shut down the Qdrant process. Using the pkill command, we safely terminate the background service, cleaning up our environment. This ensures no orphaned processes remain, keeping our system tidy after our successful demonstration of vector database operations.